This is Porterville College Physics 102B homework for Chapter 25, Nuclear Physics, starting with problem number 29. Write the isotope symbol, and the first one is 24 protons. So first you have to look up what element has 24 protons. Look that up in a table of isotopes or a periodic table, and you get that it's chromium, so the symbol is Cr. The number of protons plus neutrons gives you the atomic mass number, 49. So that'll be Cr with the 49 up top here. B, 43 protons. That tells you that it's technetium. The symbol is Tc. 43 plus 51 gives us an atomic mass number of 94. So we have the symbol here. And finally, C, 82 protons, that's lead, and 108 neutrons gives it an atomic mass number of 190, so we have lead 190. The symbol is Pb. Number 31, find the number of protons and neutrons in bromine 80. So bromine, you look it up and you find that it has 35 protons, so 80 minus 35 will give the number of neutrons, 45 neutrons. For the second one, 36 protons is krypton, so 36 protons, and then you take 80 minus the 36 protons and you get 44 neutrons. Number 33, find the nuclear radii. We use the formula in each case where the radius of the nucleus is 1.2 femtometers times the atomic mass number to the 1/3 power, or the cube root of the atomic mass number. So for lithium 7, you're going to take 1.2 femtometers times the cube root of 7 and get 2.3 femtometers. For part B, 3.3 femtometers. For C, you get 6.1 femtometers, and for part D, 7.4 femtometers. Number 35, what's the nuclide whose nuclear diameter is closest to twice that of aluminum 27 nucleus? So a bit of algebra here. I've started by saying the radius that we're looking for. First of all, if the diameter is going to be twice the diameter of aluminum, divide those by 2 and you get the radius is twice the radius of aluminum. So the radius is twice the radius of aluminum, and then you plug in the values from the previous problem that any nuclear radius is going to be 1.2 femtometers times the cube root of the atomic mass number equals twice, and now we do the same thing for the radius of aluminum. It's 1.2 times the cube root of aluminum's atomic mass number, 27. Conveniently, the 27, the cube root of that is 3. That makes the math nice and easy. You see that the 1.2's divide out, and what we're left with is the atomic mass number of the mystery nucleus. The cube root of the atomic mass number is equal to 2 times 3, which is 6. So to solve for that atomic mass number, take the cube of both sides, so you get the atomic mass number is 216. So the answer to this question is any nucleus that has an atomic mass number of 216. And some examples would be polonium 216 and radon 216. Number 47. Write the full reaction for the beta minus decay of copper 67. Here's what I recommend you do. Fill in the number of protons because we're going to do some math balancing of equations. So copper with a mass of 67 and a charge, it's the nucleus, so the charge of 29, is going to result in, and generally speaking for beta minus decay, or not generally speaking, always for beta minus decay, the mass is going to stay the same and it's going to go up 1 in atomic number. So this will become the element that has the atomic number of 30, which is zinc, and it's zinc 67. Now you should see that these numbers add up. I didn't write in the numbers for the beta minus decay. Let me write this right now. As I teach in class, you can think of the top number as being the mass. And a beta particle effectively has a mass of 0, as compared to protons and neutrons to the atomic mass unit, close enough to 0. It has a charge of -1, so I'm just going to write that right in there. And now you can see the math should add up. The numbers should add up. 67 equals 67 plus 0. There's our conservation of mass. 29 equals 30 plus -1. There's our conservation of charge. For the next ones, we have krypton 85, and remember, for beta minus decay, it's gonna stay the same mass but go up 1 in number of protons. So this gives us the element with 37 protons with it, which is rubidium. So rubidium 85 plus beta minus. Then there's going to be, what's the next one? Palladium is going to decay into the element with 47, and that's going to give us silver. You can see silver 112. Okay. Number 48, we have, this is fill in the blank. Complete the following reactions. Zinc 71 decays into gallium 71, and you have to think what's going on. So you see that it's maintaining the same mass but going up in proton number, and so that tells you it's just like all the ones in number 47. It's beta minus decay. But what can also help is realizing that whatever this thing is that we're filling in the blank, it's going to have to be 0, because it's going to have to be -1, because 30 equals 31 plus -1. And the mass, 71, equals 71 plus 0. And that tells you for sure it's going to be a beta minus. For the next one, we have germanium 66. And what's it going to decay into? Well, we see that this is a positron, which has a charge of 1 and a mass of 0. So to fill in the blank, we say 32 equals what plus 1? 31. And that's going to give us gallium. 66 equals what plus 0? 66. Excuse me. So we have gallium 66. For the next one, the next fill in the blank, we have actinium 213. What's it going to decay into when you're left with the helium nucleus? So just do the math. So 213 plus what will give 4? So that's going to be 209. With the charge, 89 plus what gives 2? So that should be 87 to conserve charge. So we're looking at francium 209. And finally, the gamma decay. For the gamma decay, it just simply comes from an excited nucleus. So this is bismuth 210. It's just going to come from an excited bismuth 210 nucleus, so we denote that with the asterisk. Number 49. Okay, more of the same. Complete the following reaction. So we have thulium 158 and it's going to have beta decay. So there's my 0 and my -1. So the mass is going to stay the same at 158. It's going to decay into something that goes down one less in atomic number. So it's going to be erbium. Erbium 158. For the next one, hafnium, it says that hafnium is going to decay, so it's giving the daughter nucleus, lutetium, and we just have to figure out what is that little particle that it's going to give off. Well, since it maintained the same mass, so you know it's going to be something with a mass of 0. This thing is going to have a charge of +1, so that 72 equals 71 plus 1, so that's going to be a positron, a beta plus. For the next one, we have francium 216, and I've just quit writing the atomic numbers. Francium 216, and it's going to decay. It's going to decay into astatine 212. Well, there's only one decay that we know of that does this, that goes, it's going to drop in mass by 4. And that's going to be a helium nucleus, so alpha decay. But you can also look it up and see francium has an atomic number of 87, astatine is 85, so it does in fact lose a charge of 2 for the helium nucleus. Then the next one, beryllium 8. You see it's giving off a helium 4. And what makes the math work out is to be another helium 4 right here. Also, you can see if I add in these atomic numbers, 4, 2, and 2. So 4 equals 2 plus 2. So 2 alpha particles right there. Number 53. What you need to know for this is the conversions of decay rate, that 1 curie is equal to 3.7 times 10 to the 10th becquerels. 1 becquerel is a decay rate equal to 1 decay per second. So we're given an amount, 4 picocuries, so 4 times 10 to the -12 curies. We want to get that in becquerels, so there's the conversion multiplied by 3.7 times 10 to the 10th becquerels per curie, and you should get 0.148 becquerels. Now keep in mind, since a becquerel is a decay per second, that means 0.148 decays per second. So then part B, we want to know how many decays per day is this. Well, we have decays per second that we got from part A, 0.148, multiplied by 86,400 seconds per day, and we get 12,800 decays per day. Number 57, medical use of radionuclides. We have oxygen 15 used in a PET scan, and it's got a half-life of 2 minutes, so it goes away, decays very quickly. We have an initial amount of 2.60 milligrams. And it says that from the time it's produced in the cyclotron to the time it's delivered, 6 minutes later, how much do you have left? So we're going to use this formula, that the amount you have, n, equals the initial amount at some 0 time, n naught, times however many half-lives have gone by. It's going to be that many powers of 1/2. So this is the formula to use. N equals n naught times 1/2 to the x power. So first we need to figure out how many half-lives have passed by. 6 minutes. A half-life is 2 minutes. And so we can do this and say the time divided by a half-life, 6 minutes divided by 2 minutes. So 3 half-lives will have passed by. So we plug that in here. N equals 2.60 milligrams times 1/2 to the 3rd power. You can see it's going to be chopping the amounts by a factor of 8. So by the time it's delivered, it's only 0.325 milligrams. Part B then asks, after another 4 minutes, it's injected into the patient. How much does the patient get? So we'll start from 0 time when it was first produced. We can say n equals the original amount, 2.60 milligrams, times 1/2 to the, and what power? Well, since it's been produced, there was the first 6 minutes, then 4 minutes later, so it's been 10 minutes over 2-minute half-life, which means 5 half-lives have gone by. So we're going to do 2.60 milligrams times 1/2 to the 5th power, which means the original amount is getting cut by a factor of 32. So we have 0.081 milligrams. Now, here in the blue ink, I've done an alternate solution. When I did part B here, I did it starting with the time when it was first produced, 10 minutes ago. We could take it from the end of part A and say it's been 4 minutes since it was delivered, and when it was delivered it was 0.325 milligrams. That's the answer we got in part A. So if we do that, we say n equals the initial amount, and again, initial now is how much was delivered, 0.325 milligrams, times 1/2 to the, and remember it's been 4 minutes, so 4 minutes divided by a half-life of 2 minutes means that 2 half-lives have gone by, and you get 0.081 milligrams. So it's the same as we get here. Either solution works. Number 63. Tritium has a half-life of 12.3 years, and we want to know how much we have if we start with 2,500 kilograms. How much would remain after 100 years? Well, first of all, let's figure out how many half-lives that goes by. So I'm going to use the same formula I used in the last problem. X equals 100 years divided by the half-life, 12.3 years, and we get about 8.13 half-lives that are going to go by. I'm now going to use this n formula. Now technically the n's refer to the number of nuclei. But you notice in this problem as well as the previous problem, they both refer to the masses, whether in milligrams or kilograms. But since the mass is proportional to the number of nuclei, we could also use this. You could use the n's also to denote mass, as I already did in the previous problem. So I'm going to let n naught be 2,500 kilograms times 1/2 to the number of half-lives that go by, 8.1301, and we get 8.92 kilograms that are left. For number 64, smoke detectors use americium-241 with a half-life of 433 years. You keep a smoke detector for 5 years. By what factor is it reduced relative to when it was new? All right. So it's good to note that the activity, R, is equal to the decay constant that's special to that isotope times the number of nuclei. And the reason I bring this up is because I haven't yet in this homework set introduced an equation for activity, but we do have an equation for nuclei. And what I want you to see is that right here, this says that activity is proportional to the number of nuclei. So if we take this equation, the n equation, multiply it through by lambda, so you get lambda n equals lambda n naught. Well, lambda n is r. Lambda n naught is r naught. So this equation, basically it comes down to this. Switch the n's for r's, and it becomes the activity equation. R equals r naught times 1/2 to the x power. we want to know about the amount of reduction, how much it's been reduced. So I'll first start by setting it up as a fraction. How much activity is there as a proportion to the initial amount? So r over r naught is 1/2 to the x power, which is 1/2 to the 5 years divided by 433 years. That's a small number, so you should guess it's going to be like in the 90s%. When you actually do the calculation, you get r over r naught is 0.99203, which means it is 99.203% of the initial amount. The question is asking how much has it been reduced. So take 1 minus that, or if you want to think of 100% minus 99.203%, that'll be how much it's produced. So 1 minus the fraction gives you 0.00797, or you could say it's 0.797% reduction. Number 64, part B, is how many years pass before the activity falls to 99%? Well, after 5 years, it had fallen down to 99.2%. So you can estimate it's going to be a little more than 5 years. Well, let's do the math here. We have r over r naught equals 1/2 to the x power. We're looking for when this fraction, r over r naught, equals 99%. So 0.99 equals 1/2 to the x power. To solve for x, we need to set it up as it's a logarithmic equation. So log base 1/2 of 0.99 equals x. Now how do we solve this kind of logarithm? Our calculator generally only has 2 logarithm keys. One is for common logarithm, the other is for natural logarithm. So if you're taking a logarithm of a different base, you do this. It's the logarithm of the number divided by the logarithm of the base. So it's log 0.99 divided by log 0.5. Also, you could do natural log of 0.99 over natural log of 0.5. As long as you do the same base logarithm, it should come out the same. It will come out the same. So you get that x is equal to 0.0145. That's how many half-lives go by. We want to know what that is in years, so multiply it by 433 years per half-life for americium 241, and you get 6.27 years. Number 71, complete the following fission reactions. So, neutron hits uranium-235 nucleus and it yields barium-144 plus something plus 3 neutrons. Okay, so do the numbers and see what the math gives. So it starts out with a total mass of 1 plus 235, there's your 236, 0 plus 92 charge, so 92. These two numbers need to be conserved. So 144 plus 3 neutrons gives 147, and you say what adds up to 147 to give 236, and you get a mass of 89. Similarly, the charges have to add up to be 92, so that'll give krypton 89 with 36 protons. For the next one, once again, the masses will add up to 236. The charges add up to 92. You see what will fit in there that makes it work, and that's lanthanum with 57 protons and a mass of 143. And the last one, the masses need to add up to 240, the charges need to add up to 94. And when you do that math, you get zirconium, which has 40 protons, and it's got to have a mass of 96. Number 93. Iodine 131. Okay. We had an initial amount of 2,900 becquerels, an initial activity. And we need to know the number of half-lives that's going to go by after 5 days. So X is going to equal 5 days divided by the half-life of iodine 131, which is 8.04 days. We get X equals 0.62189 half-lives. So the activity after 5 days is going to be R0 times 1/2 to the X power, which is 2,900 becquerels times 1/2 to the 0.62189 power. And we get an activity of 1,884 becquerels, which is less than the recommended limit of 2,000, so it can be deemed safe to drink. Now here, switching to black ink, I've done an alternate solution. Another way to do this is to solve for the time that it would take to drop down to 2,000 becquerels. And if the milk is safe to drink, then what will show that is if it takes shorter than 5 days to do that. So we have R equals R0 to the 1 times 1/2 to the X power. We're assuming the radioactivity is 2,000 becquerels, and now we're going to figure out how much time it takes to do that. So 2,000 equals 2,900 times 1/2 to the X power. In this next line, I've divided 2,000 by 2,900. I get 0.689. Or another way to say that is that the activity has dropped down to 68.97% of its original level. So this here now is a logarithmic equation. So we set up a log of base 0.5 of 0.689655 equals x, and we solve this the way we did the previous problem that involved the logarithm, that x equals the log of 0.689655 divided by the log of 0.5, and we get that x equals 0.5361 half-lives times 8.04 days, which is a half-life for iodine 131, and we get 4.3 days. And so it takes 4.3 days to drop down that low, and we're evaluating if it will have gone below 2,000 becquerels in 5 days, and yes, it'll do that before the 5 days. And that concludes the Chapter 25 homework.